So I was asked to talk a little bit about our development of next generation focused ultrasound systems for brain treatments. And the first question, of course, is why do we need next generation helmet? We have the InsideTech device that works well. It can ablate nicely inside brain, in the middle of the brain for tumor treatments, and it can modulate the blood-brain barrier very precisely throughout the brain. So why do we need next generation system? First of all, the current device can ablate only in the center of the brain. So it would be advantageous to have a device that can ablate throughout the brain. Second, MRI is fairly expensive, and tying the scanner for a long time is expensive and cannot be applied everywhere on the globe. And third, the system uses pin fixation to the scalp bone, so it's not very pleasant and not reproducible, for example, if daily treatments are needed. So what is our goal in the next generation device? Our aim is to ablate throughout the brain, be able to do multiple treatments, be able to control microbial activity such a way that we can do it outside the MRI scanner, and that way make the system portable and low cost. So for the past 10 years or so, we have been developing different phase array transducers for testing different ideas for treating brain tumors and brain tissue. And this is one of the arrays where we have three transmit-receive elements. So each of these could be used for transmitting or receiving. And typically what we do, we transmit 600 kilohertz, listen at 300 kilohertz for subharmonic, or 1.2 for second harmonic. And these modules are distributed along a hemispherical surface based on computer simulation optimized array design, parts array design. It allows complete electronic steering of the beam. And here is an example of rapid brain in vivo experiment where we are sonicating along the script pattern, and we are sonicking in this location and listening the signals coming out. And you can see that we can construct the beam profile nicely across the beam and along the beam at the whole three-dimensional volume. And then by scanning this beam in a controlled manner, we can have very nicely tailored uniform blood-brain barrier enhancement. So can this system now be used to ablate tissue? We use the bubble signals that we received, and we are constructing the spectral information and listening to the subharmonic signal and ramping the pressure amplitude up until we receive the subharmonic signal. And when we see that, we either keep the power pressure amplitude the same or increase by 150%, so it's 150% of that level. And here you can see now the subharmonic activity as a function of time, and we can form the signals coming from the bubbles and each of the sonication locations, and then use that to try to come up with the algorithm that allows us to predict where the tissue damage happens. And so we have this time information where each location, we have the spectral information. Here you can see subharmonic signal, and then we can form the four-dimensional maps of the bubble activity. And from that, we can calculate the tissue damage. So here is now, from many animal experiments, the tissue volume that was damaged, and here is the exposure level. So at the lower levels, we don't see any tissue damage. 100% level, we start seeing some tissue damage. 150% level, we have a nice tissue damage, and you can notice that both the histological tissue volume and the MR-derived tissue volume and the passive acoustic map tissue volume are almost equal. So it looks like we can use the passive acoustic mapping to tell what tissue volume was damaged. And here is now a better graph where it shows the damaged tissue volume as a function of acoustic imaging volume. And you can see that we have very good correlation between the MR and the histological size of the tissue damage. So it seemed to work relatively well. And when we analyze the bubble activity during the 10 millisecond pulse, we can see that we get a fairly good correlation between the lesion size and volume in different cases. But if you analyze only this signal from part of the acoustic pulse, then the correlation is not as good. So we need to capture the whole signal and then analyze it to be able to get good correlation. And if you do that, our positive predictive value is really good. And we can pretty much predict how the lesion is going to be formed and definitely where it's going to be formed and if it's going to be formed. So that's the monitoring. It looks promising. What about how can we get rid of the pins? For that, we have developed a technique where we take CT scans or MR scans, both of the patient, in this case as a skull, and then use those to print a helmet, custom helmet that fits snugly around the head. And then use computer simulation to optimize locations where we can put transmitters such a way that we have an optimal configuration for the therapy that is needed. And we have built such a device with 4,000 transducer elements. Here you see the actual helmet that has been printed to fitting around ex-vivo human skull. And you can see these transducer modules. Each of these little squares has 64 transducer elements. And we have tested this now with the human skull. So this is now human skull. We have decast water here, and then we put a rat, in vivo rat brain that we're sonicating here, and use the signals to control it. So what we did in this experiment, we ramped up the pressure amplitude until we saw subharmonic emission, and then we dropped the pressure amplitude to half, so we can have just a blood-brain barrier opening. And here you can see the subharmonic signal, no focal location, so there is no signal coming from the bubbles. And then when we reach this threshold where we see the subharmonic, you can see nice focus location in the target volume. And then when we look the imaging, so here is the image before, no T1 weight signal enhancement, and here is now the post. You can see a nice permeability enhancement in this location and this location, both without any tissue damage. So it looks like this is a very rough proof of principle concept, but the experiment showing that the concept itself seemed to work, and we seem to be able to use this technique to target tissues and actually control the exposures. So as a summary, ultrasound and micropulse can induce ablation that has been known for some time. And it looks like that we can capture the micropulse activity and use it to control the extent of the ablation. We can localize them, we can even super localize them, and we can use the spectral information to control the bio effect. We can use rapid prototyping techniques to build custom helmet so that we don't need online MRI. But this, of course, is very early, and we need more work to translate this technology to clinic. And finally, I'd like to just thank my group. There are many people who have been involved in this research over the past few years, and found funding, especially from Western Brain Institute and Cerebral Foundation, and then many collaborators.